Okay, so in this problem, I've got a box. It's got a frictionless movable piston in between two things of air. Okay, and each side has got its own properties. Okay, so I want to figure, I'm going to let go of this piston. It'll move around. I want to figure out once it comes to equilibrium, what's the final temperature, what's the final pressure, and then what is the entropy production. Okay, so before I get started, I'm going to go ahead and figure out the properties necessary for each side of the box here. Okay, so what I'm going to go and do is, first thing is I'll use, we'll call this 1, we'll call this one 2. I'll go through and I will find the masses, mass 1 and mass 2. Okay, in doing that, what I'm going to do is I'm going to use my ideal gas model, PV equals mRT, for air that I have here. Okay, so what I'll do is I'll solve for m. That means m1, for example, is going to be that'll be 4 bar, so 4 times 10 to the 5th times v, which is 1.5 cubic meters, divided by r, which is 8314, divided by 28.97 for air. Okay, and then my temperature is 400. Okay, so from that I can find that M1 is 5.227, and that'll be kilograms. Okay, M2, everything's exactly the same except for my bar, my pressure is half of it. So this mass is going to be half of this mass, because the only thing that changes in the equation is this goes from 4 to 2, because the volumes are equal, the temperatures are equal. Okay, so that means the amount of mass in 2 is 2.613 kilograms. Okay, so again, same equation, just plugging in 2 instead of 4 there. Okay, now, okay, in order to find that temperature and entropy production, okay, I'm going to ultimately, let's talk about the temperature. I'm ultimately going to have the first law equation, which is that delta U equals Q minus W. I'll get into that in a second. Let me go ahead and look up U1. Okay. Now, notice that for U, it depends only on temperature, remember, for air. Okay. These temperatures are the same. They're both 400. That means U1 equals U2, which equals, for 400, 286.16. Okay? So those have the same energy initially. Okay, I'm ultimately looking for entropy production. So let me go ahead and look up S01 and recognize again, because the temperatures are the same, that's going to equal S02. Now this is not the actual entropy. Again, this is that entropy at a specific value, okay? Because the total entropy depends not only on temperature, but also pressure. But this S0 value, again, is going to be the same. It's going to be 1.99194. Again, both sides are going to be the same. They're at the same temperature, so U and S0 are going to be the same for these. Okay. Going back to my first law equation, now I know that Q, okay, to the surroundings is 0. There's no heat loss. I mean, there might be some heat interaction between these two sides, but there's not going to be any to the surroundings. So for the total system, there's no heat transfer. Okay. Same thing with work. Again, this guy might move around a little bit, but that's internal. That's part of my system. So the work is also 0. Therefore, the change in U is 0. Okay. So what does that mean exactly? Okay. Well, essentially, it means that the initial minus the final equals 0, which means my initial M1U, well, that's my initial. Okay. I actually want my final. Okay. Everybody, hopefully we can understand that at the end, my U final on both sides are going to be the same. So UF1 equals UF2, so I'll just call that my final. right? Because when they come to equilibrium, they're going to come to the same energy. Okay, so what that means then is that M1 UF minus M1 U1, okay, plus M2 UF minus M2 U2. That all has to equal 0, right? This is, this is delta U of the left side. This is delta U of the right side. The bottom line is, if these two are the same, okay, and these two are the same, okay, then they're all of the same, which means that U final equals U1 equals U2. Okay, for these to equal 0, that's what has to be the case here. Okay, which means the temperature is also the same, which means temperature final equals 400. Now, that was a whole lot of unnecessary math to recognize these are at the same temperature. So when they reach equilibrium, they're going to reach the same equilibrium temperature. Okay, so that final temperature is going to be 400 Kelvin. Okay, now that I have that final temperature, I can find the final pressure just using the ideal gas model again. Okay, where I'm going to have my mass, M1, which was 5.227 plus 2.613. Again, that's the total mass, okay, times R, which again is 8314 divided by 28.97, times the final temperature, which is 400. Okay, because again, when they reach to this, the pressures are going to be the same on either side. It's going to be, all the properties are going to be the same. So the total pressure again is going to be the total mass at its temperature and volume, and the total volume then is 3. Okay, because that's the total volume, meaning that final pressure, when I plug that in, is actually 3 bar. And again, that makes sense. And this is going to come to an equilibrium halfway between those 2 bars, since there's no heat transfer or anything like that. There's no change in temperature. Okay, that pressure is just going to equal out here. Okay, now my second law equation, okay, again is delta S equals Q over T plus sigma. Now that goes to 0. Okay, which means my entropy production is my change in S. Okay, now my change in S for air is going to be M1 times delta S naught 1 minus R times the natural log of P final over P1 plus M2 times delta S2 naught minus R times the natural log of P final minus P2. Now again, what I have here, okay, is we have these S naught values. Remember, my actual delta S is that S naught, the change in that S naught, plus this term that deals with pressure. Okay. Now, these S naught values, these actually go to 0, right? Because, again, there's no change in temperature. Okay? So the change in those S naught values are the same. Now, there is a change in the pressure here. So I need to take into account that. Okay? Because this one goes from 4 to 3, this one goes from 2 to 3. Okay? So plugging in those values, I get 5.227 times negative R, which is 8.314 over 28.97 times the natural log of the final 3 over 4 plus M2, which is 2.613 times a negative 8.314 all over 28.97 times the natural log, and this time it's 3 over 2, which means that entropy production, again, is that change in S, which again, S naught has no change. It's just that change due to the pressure. And I get this equal to 0.1274 kilojoules per Kelvin. Okay, so again, no change in temperature because they both start at the same temperature. Pressure equilibrium in between those two, and then my entropy production is, again, because there is no heat transfer, delta S is the change in entropy. And delta S for air is that S naught minus R natural log of the pressure ratio. S naughts are 0 because, again, there's no change in temperature. So I just have these pressure ratio, plug those values in, and there you have it.